Hello. In this lesson we're going to see how we can use components of vectors to solve problems. I'm going to go through a couple of worked examples in detail so you can see how it's done. You do need some background information. You should already know how to resolve a vector into two perpendicular components. There is a separate lesson about this, but I will spend a few moments just recapping. You should also know how to add two perpendicular vectors using Pythagoras and the inverse tangent. Again, there's a lesson about this, but I'll spend a few moments just reminding you. So let's just go over a couple of things you should already know. First of all, how to resolve a vector into two perpendicular components. Suppose we've got a vector v, and suppose these purple lines represent the vertical. V makes an angle of theta to the vertical. How can we split V into a vertical component and a horizontal component? Well, we construct a rectangle which has V as its diagonal. One side is the vertical component and the other side is the horizontal component. The magnitude of the vertical component is simply the magnitude of V times cos theta. And for neatness, we'll write that as simply V cos theta. The horizontal component is V sin theta. I'm hoping you're already familiar with this. How do we add two perpendicular vectors? Say A and B. First of all, position them so their tails are touching. Construct the rectangle with the vectors as the sides. The resultant is the diagonal. Suppose it makes an angle theta to vector B. I can work out the magnitude of the resultant. It's the square root of the magnitude of A squared plus the magnitude of B squared. And this angle theta, it's tan minus 1 of magnitude of A divided by magnitude of B. Tan minus 1 means the angle whose tangent is whatever this number comes to. Again, I'm hoping you're already familiar with this. Let's do an actual problem using components. What we're going to do is add three coplanar vectors. Coplanar means in the same plane. So we're looking at a two-dimensional problem on a flat surface, not 3 dimensions. Coplanar in the same plane. So here's an object shown in blue, and here are three vectors acting on it, three forces. And I want to know what the resultant force is. Let's put some numbers in. So there are the magnitudes of each vector, and I've given the angles relative to the object here. It's convenient to talk about some directions. We don't necessarily have to have horizontal and vertical. Let's keep it further general by having an x and y direction. As in an ordinary graph, positive x to the right, negative x to the left, positive y upwards and negative y downwards. The strategy for solving the problem, for finding the resultant, is this. Step 1, find the total of the x components. Step 2, find the total of the y components. And then step 3, we combine these two totals by vector addition, and that gives us the resultant. Let's do it. There's the original problem. We want the components of these forces. It can help us to draw these boxes in, though we don't normally bother. I hope you can see, for example, looking at the top box here, the vertical component, I should say the y component to be precise, the y component will be 15 times cos 50 degrees. And the x component, which will be to the left at negative x, will be minus 15 sine 50. So we can draw these boxes if it helps us, but it's usual not to draw the boxes, just to be able to write down the components as 15 cos or 15 sine, for example. So let's get rid of the boxes and work through and find all the x components first. And here they are. Start with the yellow force, 25 newtons. The x component, that's a part of it to the right, is plus, because it's to the right, 25 sine 70. The red force, as an x component, to the left. So its magnitude is minus 15 sine 50. The green force has also got an x component to the left, so its x component is minus 16 times sine 20. The numbers get put into your calculator, and when we work it out, it's 6.53 newtons, and that's the total of all the x components added together, taking into account their direction. We do exactly the same sort of thing for the y components. For the yellow force, the y component is downwards. I hope you can see that. It's minus 25 cos 70. For the red force, the y component is upwards. It's 15 cos 50. And for the green force, the y component is downwards. Minus 16 cos 20. Again, work it out, add them up, and it comes to minus 13.95 newtons. So we know the total x components and the total y components. The last bit is fairly straightforward. Our total x components is 6.53 newtons, total y is minus 13.95 newtons. We add those two together by vector addition. The resultant is that diagonal. We can use Pythagoras because the vectors are perpendicular. The magnitude of the resultant is the square root of 6.53 squared plus 13.95 squared. It comes to 15.4 newtons. And if we want the angle to the vertical, or I should say to the y-axis, this angle theta, it's tan minus 1, 6.53 over 13.95. Notice the tangent of the angle is that distance, the bottom distance over the side distance. So the inverse tangent is tan minus 1, 6.53 over 13.95. Ignore the minus sign, it doesn't affect the calculation of that angle. So we've added our three original vectors together, and this is the resultant and its magnitude and direction by using the components. A bit fiddly, but not too difficult. Let's try another problem. This is a typical simple textbook problem. Let's read it out. An object of weight 100 newtons is supported by two ropes at 72 degrees to the vertical. The tension in each rope is T. The resultant force on the object is 0, which of course means it's in equilibrium. It's just an object hanging from two ropes, stationary object hanging from two ropes. And look at the diagram that shows the setup. The weight is downwards, so we should really mark it as minus 100 newtons downwards. Two ropes with tension T and an angle of 72 degrees. Notice this is symmetrical about the vertical axis. That's very important. It will simplify the problem. Symmetry often simplifies problems. Let's answer the first question. Write an expression for the force exerted by the ropes. Well, I hope you can see that the vertical component of tension is T cos 72 degrees, the vertical component of tension. The horizontal component of tension will be T sine 72, but that will be cancelled out by the horizontal component on the other side. T sine 72 to the right will be cancelled by T sine 72 to the left. So because of the symmetry, we can say immediately that the horizontal components cancel. We want an expression for the force exerted by the ropes. Well, it's just the two upwards components. The force exerted by the ropes is twice T cos 72. The last part is find the tension T. We know the object is in equilibrium, its resultant is 0, so we know that the upward force T cos 72 plus the downward force, which is minus 100, they must add up to 0. T cos 72 equals 100. If we solve that, it gives T is 50 over cos 72, which is 162 newtons. That's it. That's a couple of examples, should give you a good flavour of how we should use components to solve some problems. I'd like to point out that we've only talked about two-dimensional problems, so everything in the plane. It can be extended to 3 dimensions. And for anyone interested in the mathematics, I will make a note here that in 3 dimensions the magnitude of the resultant is the square root of x component squared plus y component squared plus z component squared. And we can get the direction of the resultant by using things called direction cosines, which can be found by using something called a dot product. Now, if you're not doing mathematics, don't worry about that. I merely mention that in case anyone is interested in how you cope with 3 dimensions. And that's all I want to say, so thank you for watching.